Hey there, and thanks for tuning in to our presentation of which integrable projection is which, presented by Josh Vector. So the problem that we'll be talking about comes up in many different areas in geometry processing and computer graphics. So for instance, let's say that you're tasked with the problem of making a bunny look like a cactus. Or suppose you design a 3D model and you want to find an alternative representation of your geometry that's suitable for efficient physical simulation. Or suppose you more directly want to use a texture for computational fabrication purposes, such as in topology optimization, where you have a limited amount of material that you want to distribute most efficiently inside of some geometry. This last area is what brought us to think about these problems. We were specifically thinking about the problem of inverse basket weaving. So suppose that you have you see some geometry, some object in nature, like this seahorse. There exist pretty good tools for turning the object that you see into a 3D model. And we asked, well, could you take that 3D model and weave something out of ribbons to resemble that geometry? And after spending quite a bit of time developing a pipeline, we arrived at this, which lets you take an arbitrary 3D model, like this Stanford bunny, and generate instructions to fabricate it in real life out of ribbons. Okay, so that's 4 different kind of variations on a theme. So what is the theme? The theme is that all of these applications all use the same mathematical machinery of studying fields of various sorts on 2 manifolds or 3 manifolds. And so there's some caveats that I want to preface this presentation with, which is that there's many different discretizations of the smooth theory that underlies what I'll be presenting, and there's not really one right answer. And also, for the purposes of this talk, we're mostly going to be talking about 2 manifolds, but the idea is generalized, specifically the formulation that we're presenting generalizes immediately to higher dimensional simplicial complices. And but I won't be focusing too much on that. Okay, so now going forward, we'll be representing our manifolds as unstructured triangle meshes, so just a list of vertices and a list of triangles. And we'll be placing scalar functions, we'll be representing scalar functions as a number per vertex of our triangle mesh, and then we'll linearly interpolate the scalar functions on the interior of each triangle. Similarly, we'll be representing vector fields as constant fields per triangle face. Okay, so now we have 2 different sorts of data. We have a scalar field, which is represented as a value, as a number per vertex, and a vector field, which is represented as here 2 numbers per triangle. And now we can start thinking about compatibility between these 2 fields. So if we start with a scalar field, we can pick one. So we assign a number per vertex, and then we linearly interpolate on the interior of each triangle. Well, this linear interpolation uniquely determines a vector per face of our triangle mesh. And this vector field is integrable, sort of by definition, because we'll take the definition of integrability of a vector field to mean that there exists some scalar field, which when you take the gradient of that field, you get your vector field back. And not all vector fields are integrable. Here, for instance, this is a simple example. We can take 2 triangles and pick a constant vector per face, and then we can linearly interpolate in order to get the representation of a scalar field for each of these triangles. But the representation of the scalar fields on the 2 triangles doesn't glue up. And if you look at the values of the scalar field along the shared edge, they agree at no point other than the initial point where you force them to agree. So from here you might ask, well, is there some nice characterization of when a vector field is a scalar, or when a vector field is integrable? And it turns out that there is. in 2003, Poltier and Persus introduced this definition of local vector field integrability, which says that if you have a vector field, here u and v, we want, in order for this field to be integrable, the projections of u and v on the shared triangle edge must agree. And they proved this theorem that said that discrete fields satisfying this condition on simply connected domains are integrable. This is not true on not simply connected domains, as we'll see in a second, but for simply connected domains, their proof amounts to saying that you just pick a spanning tree and you flood fill the values across all of the vertices, and they just prove that independent of your choice of spanning tree, you'll always get the same scalar field back. And what's nice about this definition is it immediately generalizes to higher dimensions, where it just introduces an extra linear constraint per shared facet for each extra dimension that you add. And so now that we have this condition, we can note that integrability represented in this way is a linear constraint per shared edge. So we can write down a projection. And this, by saying that, like, given a vector field W, we can look for the smallest displacement from our field, which satisfies this linear constraint per edge. And this is a convex problem. It's just a linearly constrained quadratic program. And it's also a funny way of writing down something known as the Hodge decomposition, which is something that has been very well studied in a number of contexts, which says that given an arbitrary vector field on a manifold, you can always decompose it into the sum of an exact form, a coexact form, and a harmonic form. And this gives us a projection onto the exact or curl-free component of an arbitrary vector field. But there's a global obstruction, which is that this only works for simply connected domains. So if you want to work on a not simply connected domain, let's just see what goes wrong on a not simply connected domain. So let's consider a constant vector field on a circle. When is this constant field integrable? Well, if we try to assign a constant number per node in our circle, everything's fine and good until you get back to where you started, in which case the only time that you'll ever agree is if your constant field was uniformly 0. This is a bit restrictive, so we now can modify our definition of integrability to, instead of saying that our scalar field is represented as a real number per node, we'll instead represent a circle valued number per node, so an S1 value over our surface. And this gives us a little bit more flexibility in the sort of functions that we can represent on these sort of complicated surfaces. And there's a nice machinery for thinking about circle-valued functions over surfaces, which is the idea of a foliation. So given an arbitrary manifold, a foliation is a decomposition of the manifold into a union of submanifolds called leaves, which all glue together to get the original manifold back. And for the purposes of this talk, we'll be thinking about taking our manifold and coloring each point with a value on a circle, and then our leaves will just be level sets of constant color. So now that we've defined what a foliation is, let's consider this specific foliation. This is a foliation because we have a circle and we've assigned color to every point on the color wheel. And now we can look at the direction that the color is changing at each point. And this gives you a bunch of concentric circles. And now we can think of the unit field that's aligned with this direction field. Well, this vector field is not integrable. Why is it not integrable? Because another definition of integrability is that your loop integrals must agree. And in this case, a unit integral around the loop is always the same, but the length of the outer loop is longer than the inner loop, so the integrals are clearly not the same. However, this rescaling of that unit field is integrable, and so this is now a different notion of integrable projection. Here we're looking for a projection that didn't change the input direction field, the input field direction. Okay, so here we come into contact with the fact that things might be slightly subtle here. So if you have an input direction field and you want to find an integrable field that's aligned to it, this gives you a stripe pattern. But there might be additional constraints which you might want to place on a field on a surface. For instance, you might want fields which are everywhere smooth and approximately unit. And maybe you want to enforce multiple conditions at the same time. If you want to enforce both of these conditions, well, this is exactly the problem that we studied when we were trying to weave arbitrary structures out of ribbons. And it turns out that there's a nice mathematical way of understanding these ideas, which is, and more than just a mathematical way, the thing that we're about to present is convenient from a computational standpoint too, and immediately yields efficient algorithms. So just to recall from the previous slides, this was our formulation of a Hodge decomposition, where you just had to solve a least squares problem in order to project to the closest integrable field. On the other hand, suppose that you want to consider the problem that we considered on the previous slide, where you want to find the field which is closest to all possible rescalings of your input field. Well, this can be phrased as a problem which can be solved as a smallest eigenvalue problem. And here's a third variation on the theme. Suppose you want a field which is everywhere as close to unit as possible, while also being integrable. Well, this gives you a geodesic optimization. So now let's think in the time remaining, let's dissect this third formulation a little bit more. So in the mathematical physics literature, there's the idea of a Ginzburg-Landau functional. So there's an idea that in many settings, it's interesting to look for fields which are everywhere approximately unit norm and smooth. For instance, one place that this idea has popped up recently is in the context of finding good quad meshes of complicated shapes. So how do you break up a shape into approximately quadrilateral regions in a way that minimizes the distortion and has a small number of elements? And in practice, the way to solve this problem is using an algorithm called MBO. And how does MBO work? Well, it basically, it's a two-step process which you do a smooth diffusion followed by a rounding step. And what we're going to point out now is that there's another functional called the Aviles-Giga Functional that has been studied more recently in the mathematical physics literature. And it's basically the same as the Ginzburg-Landau functional, only now instead of just looking for fields which are approximately smooth, which are approximately unit and smooth, you ask for the fields to also be integrable. And minimizers of this functional have a very different flavor than the minimizers of the Ginzburg-Landau functional. In particular, they allow for very complicated singular structures to emerge. And this is why this functional was originally studied in the liquid crystal literature. Okay, so we added an integrability constraint. Well, it turns out that this Aviles-Giga functional is very similar to this third integrable projection that we presented just a few slides ago. You still have this smoothness term, and you also have this approximate unit term, although this is formulated slightly differently. And what we're about to show is that there's an efficient numerical technique for finding minimizers of this the latter form. So how do you find minimizers of this otherwise non-convex system? Well, it turns out that the way that this problem is formulated, it splits very nicely. You can first solve for delta while fixing the input field, the input vector field, and this is a convex problem. If you look carefully, it's just a linearly constrained quadratic program. And then all the non-convexity you can it gets encoded in the second step, which is formulated as just a direct update, because you can prove by the triangle inequality that you can just rotate your field to coincide with the points that you got from the previous linear solve. And then you can just iterate this procedure in order to get it to converge to some minimizer. And you can prove that each step of this optimization reduces the global objective function, so it must converge. Further, if you look at what happens when you study the solutions of these problems in the sharp limit, you'll see that you get these sort of domain wall singularities emerging, as also appear when people study the Aviles-Giga functional. And as a final example, if you introduce handle constraints, you can see that in the sharp limit you get this sort of fracturing behavior, where the unit norm violation concentrates along these lower dimensional features. Okay, and that was our talk. Thank you for listening. Please let us know if you have any questions.